Welcome to our channel. Please subscribe for more updates. Cambridge International AS and A-Level Physics Coursebook by David Sang et al. Chapter 20, Oscillations, Exam Style Questions. In number 1, we will just highlight the values given. This is the frequency and you have to give in the mass. Letter A. So for letter A, you are going to define what is simple harmonic motion. I'll just explain. Acceleration is directly proportional to displacement and is always opposite to the direction of the displacement. Number 2, calculate the frequency. So the frequency is simply given here. It's 4,200. It's 4,200. We expressed this in terms of seconds. So 4,200 divided by 60 is around 70 hertz. All right, that's the answer. Let's go to C. The amplitude of the oscillation is 12.5 centimeter. So that is your X sub O. So given here XO is equal to 12.5, okay, centimeter. All right. Now calculate the maximum speed. All right. The maximum speed is simply the formula. Calculate the maximum speed CII. All right. Maximum speed is as VO is equal to omega times XO. So you have your XO here. You change it into meter, and omega, you can calculate omega by 2 times F. So by doing this, you can have the omega, which is around 440 radian per second. Now, you have your omega. You have omega, you have your X sub O. You can calculate V sub O. Now, V sub O, using those numbers, it will give you around 55 meter per second. All right. Next is that, what about the maximum acceleration here? So let's go to II. Maximum acceleration, the formula is equal to minus, remember, the acceleration is always opposite to the displacement, X sub O. We have X sub O, change it into meter only. And then you have your value of the omega, square that one, calculate it. You can have around 24,000 meter per second square. Okay, now what about the force required on the piston to produce the maximum acceleration? Just use the word MA from the second law. F equals M times A. The mass is given here, 0.24, and you have your acceleration calculated. So the mass is around 5,800 Newton. That's it. Let's go to number 2. Okay, number 2. So in this case, you have attached to a distance 15 centimeter from the center. So automatically you have your X sub O. All right? This is your X sub O, or simply the amplitude. Okay? It's eliminated from the side. The shadow is cast on the screen. Symbol is placed behind the turntable rotating from the rod. The speed of rotation when it's rotating is 1.5 revolution per second. So this is your frequency. Your frequency is equal to 1.5 hertz. All right? It's your frequency. Now you can calculate now your omega in this case. So your omega, because we will explain it later on, omega is 2 pi times F. So your omega here is just actually 3 pi. Take note, we'll be using this omega later on. So times 3 pi. That's right. Now, explain what is meant by term in phase. In phase means the waves are exactly in step with each other. So the word is in step with each other. Okay? That is in phase. Let's go to B. In letter B, write down the equation to describe the displacement of the pendulum, position, angular frequency, and etc. So, can we have this here for letter B? I'll just write for letter B. The original equation is X displacement at any point in time can be calculated using XO sine WT. We know this particular formula. Now putting all the values, we have XO is 15 here. So 15 is our XO maximum amplitude. It is in centimeter. Sine. And omega is given 3 pi. So you can say 3 pi times T. Then this is now the equation that is asked for letter B. Now let's go to letter C. The turntable rotates 60 degrees from the position of maximum displacement. So maximum displacement is, I show you the picture. The maximum displacement is here. Okay, this is your XO. And then from here, it moves like that going this way. Yeah? So the equilibrium position is in the middle. This is your equilibrium position, right? So what it says here, the turntable rotates 60 degrees from the position of maximum displacement shown in the diagram. Okay? Now calculate the displacement from its equilibrium. So it means to say if it is 60 degrees from here, so if we calculate it from the equilibrium position, it will give us 30. Yeah, not 60, but 30, because we are instructed to calculate it from the equilibrium position. So here for letter C, we know the formula, okay? The formula for angular frequency is phi, or delta phi all over t. So your position now is equal to Wt. So, meaning to say your value of Wt is actually 30 degrees. Yeah, this is now your position here. This is your phi, value of phi. Now, this is from circular motion. Now let's go to the equation. What is the equation now? The equation is x, the displacement from the equilibrium. X is equals to x sub O sinus Wt. So, now your x is equals to 15 and sinus 30. And using your calculator, let me check that one. Sinus 30 is equals to 0.5. So it means to say your x is 7.5 centimeter. This is the displacement here. What about the calculate the speed at this point? Okay, the speed at this point we need to calculate. Let's go to D. So there are two ways to calculate here. Let me present you the first one. The first one is V is equal to omega. We know the omega, the value of omega is 3 pi. So omega multiplied by x sub O square minus x square. So x sub O is this is 15 and this is 7.5. Yeah, you need to square that one. Multiplied by the value of omega, which is 3 pi. Okay, 3 pi. So you can get the velocity. The velocity is around 120 centimeter per second. Yeah, you can change it to meter per second if you want. Now the other formula is using the formula, of course, the velocity at any point in time is the maximum velocity cos Wt. Okay, but we know the formula of this one, VO, it is WXO, right? It is WX times O. Right? Then cosine Wt. Wt is also given. Your XO is given. Your alpha is given. It will give you the same answer, which is 122, which is rounded off to 120 centimeter per second. All right? That is number 2. Let's go to number 3. Number 3. Okay? Number 3 is that when a cricket ball hits a cricket bat at a high speed, it can cause a standing wave to form on the bat. In one such example, the handle of the bat moves with a frequency. You have your F is given with an amplitude 2.8 millimeter. So this is 2.8. This is your X sub O or amplitude times 10 to minus 3 meters. Okay. The vibrational movement of the bat handle can be modeled in simple harmonic motion. State the conditions for the simple harmonic motion. Okay, so we need to state the condition. So the condition is that there must be vibration or vibrations where there is acceleration, and the acceleration is acting opposite to the displacement, and that acceleration is proportional to the displacement as well. That is the condition. Now let's go to B. Calculate the maximum acceleration. So letter B, the maximum acceleration will be, acceleration is equals to minus square XO square. Do we have XO? Yes. Do you have the W? Yes. We can calculate W is equals to 2 pi times F. So your F is 60, right? This is 60. And this 2 pi is 6.28. This is 6.28. You multiply that one. Then you can calculate your W. Then you apply that W here, then you square times, sorry, this is not X square, it's only W square XO. Okay, let me erase this square here. that, right? The formula must only be XO. So using these values of W, you square that one here, your acceleration will be around, 397, yeah? Or you can round this off to 400 meter second square. Yeah? That is your letter B. That's maximum. Letter C. Given that part of the bat handle held by the cricketer has a mass of this one, calculate the maximum force. So the mass is given 0.48, so it means to say just use the equation F is equals to ma. You have your acceleration here. The mass is also given, so without a problem, you do calculation. Your force is around 192 Newton, or rounded off to 190 Newton. Okay? Now, the oscillations are damped and die away about 5 complete cycles. Sketch a displacement time graph to show the oscillations. So we need to sketch that one, only 5. Okay, maybe here. You need to sketch for letter D. Sketch. Okay, only 5. So if this is your maximum on the other side, displacement. So we can have maximum here. Sketch and then getting slow. 2, 3, 4, 5. Yeah? So that is a damped, oscillation. So remember that your T here, your period, make sure that your period is still the same. So I didn't put the marking for the period, but the period must be exactly the same. You have the idea that it is damped. Okay, let's go to number 4. For number 4 is the last question here. Okay? Number 4. Seismometers are used to detect and measure the shock waves which travels through the earth, okay, due to earthquakes. So this is the setup, okay, that's the setup. Now, letter A, the typical frequency of shock wave is between 30 to 40 hertz. Explain why the natural frequency of the spring mass system in the seismometer should be very less than this range. So let me explain to you letter A. Now, in letter A, okay, if the natural frequency matches with the driving frequency, resonance will occur. So this is natural frequency, Fn, this is driving. Resonance will occur. And if resonance will occur, it will give us false. It will give us a false reading for the strength of the shock wave. So we are actually taking the reading of the shock wave. Okay, that is the reasoning there. Let's go to B. The graph in figure number 2 shows the acceleration. So this is particular graph of the mass against its displacement when the seismometer is recording an earthquake. What evidence does the graph give the motion is simple harmonic? So here we can see that the acceleration is directly proportional to displacement. Okay, it is directly proportional to displacement. What is the other evidence that we have? And it is opposite. Yeah, when A is opposite to D, so there's this negative, it's opposite. When the amplitude is positive, the acceleration is negative. It's here, yeah. But when the displacement is negative, the acceleration is positive. So that is the two evidence that you can use. Now, what about C, the last one? Use information from the graph to calculate frequency of the oscillation. Frequency, using this data, what data do you have there? You have your acceleration maximum. You also have your XO maximum. So, calculate the frequency. We know that acceleration is equal to minus square XO. That's right. So, frequency from there, W, we can say it's equal to acceleration all over XO. And then what is acceleration here? It's 40. That's right. And your maximum displacement is 8. So that is 8 times 10 to minus 2. Then you can get your W. W is around 22.3. Now you proceed now to W. W is 2 pi times F. So F is simply 22.3 divided by 2 times pi. 2 pi is 6.28. Dividing that, it will give you around 3.6 hertz. Right? This is the final answer. Until next time, thank you.